Yeah, so hi everyone, I'm Boyd and nice to have you sitting here and to come to this talk. So basically I will be talking about blockchain and Web3, which are hot buzzwords in the previous year. So you might be wondering why I would deliver this talk in this Web2 centric conference. And out of surprise, Web2 and 3 has shared a lot of similarities with concepts that we have been familiar with, the front end and the back end part. So today I will mainly focus on the backend part. As for the front end part, you can literally try anything that you have learned during this 2 days conference, and you will know why later. So hi again, I'm Boyd, and I am currently working for a security startup in Taiwan as a senior cybersecurity researcher. Our company takes advantage of both artificial intelligence and open source intelligence to help our customers identify, detect, and prevent possible threats in advance. Besides, I'm also one of the members of ChangeRoot, which is a local group in Taiwan, and holding the HackerCon every year. So I'm mainly focusing on web security and edge security for now. Blockchain security is what I'm learning and mastering right now. I have experience in giving talks at many security conferences before, such as OWASP AppSecEU 2019, HackerOne, HackerCon 2020, HackerCon, and more. So this is the outline for this session. Firstly, I will briefly introduce to you what blockchain and Web3 are. For people who are not familiar with these terms, you will know better about what they are in this section. And then I will go for smart contracts, which is one of the most important functions in the blockchain industry. I'm going to show you what a smart contract is and why it is so crucial to the industry and to the community. Then I will talk about how we do reverse engineering upon them. Starting from instructions, we will do reverse engineering by dissecting smart contracts step by step, and eventually have a clear view of its workflow and logics. At the end, to sum up what we have learned and achieved in this talk, we will demonstrate some cases, and we're going to reverse them a bit and see how we can improve our tools eventually in the future. So before we go deeper to topics pertaining to blockchain and Web3, we must understand what they are. So the first blockchain instance is what we have already heard of for years, Bitcoin, the first cryptocurrency, which was invented in 2008 by an unknown person or a group of people using the name Satoshi Nakamoto. So the term blockchain was invented due to the release of the white paper. It introduced fundamental cores such as peer-to-peer network and consensus algorithm, and we will focus on these two later. Consequently, DLT is there to cover technologies having high levels of transparency, integrity, and availability in a decentralized environment. Blockchain is one of them, obviously. So we use many social networks nowadays, and they are Facebook, Google, Instagram, you name it. They are indeed Web2, focusing on sharing data and content, among others. But where are these data stored? Normally, they are stored in centralized nodes and kept as binary data. Once there like power outage events or unexpected incidents happened, you will not be able to access this content, this data for the moment, or for good. However, as for Web3, everyone has their data stored in decentralized node. Everyone can be part of the network. There will be no one proprietarily having your identity and data that you have no control entirely. There's no single point of failure in Web3. As for the consensus algorithm, it's the most important component for a blockchain that ensures the safety of a network. It is not that easy to explain to you in just one or two sentences, but to put it simply, every participant in this network that helps the blockchain work in the way it is designed should firstly have them verified as a net trusted entity by solving the hard problem or staking valuable asset. Because of the lose in terms of sacrifice beforehand, they will tend to not to be bad guys and earn rewards after packaging transactions into blocks to recover their losses. We have several algorithms nowadays to support blockchains. Proof of work is the most classic one that is used in Bitcoin, and by averting miners from mining blocks, which is actually a procedure, participants solving complex puzzles like the GIF here, with computing powers that requires huge amounts of energy. It is accused of being a great cost to the environment. And that is why we have other alternatives nowadays that doesn't need to waste energy. So how does blockchain actually work? Here is the diagram showing how the blockchain works, and this is from Bitcoin blockchain. As you can see, a block includes a number of unconfirmed transactions in the network. After verifying by a node, namely a participant, a new verified block will be chained to the end of the blockchain, and that is why we call it blockchain. So what is so important in this procedure is that there's no need for any third parties to get involved due to the beauty of cryptography. And once a new block is generated and chained, the information will be broadcasted to nodes nearby, and eventually the whole network will receive the updates information and get synced together. So that means each piece of data is stored in each node, so everyone can read it. The information is there and cannot be referred back. This is the decentralized part that we talk about. Blockchain technology has evolved over the years into a much more mature technology. The first generation is Bitcoin, which is mainly used as a payment system. However, it is not so practical in reality because it could only process 7 transactions per second, while the current payment system running credit cards could do 24,000 transactions per second. It's a huge gap. The second generation is Ethereum, which we will discuss more in the following pages. As for the next generations, it might integrate itself with other promising technologies such as IoT and artificial intelligence, as their underlying storing or processing there. So let's talk about Ethereum, why it is so famous. Ethereum blockchain is a game changer by introducing a new function called smart contract, and rapidly becoming one of the most important blockchains till now. Why? Because by giving developers power to define rules and logics for smart contracts, similar applications can be realized with blockchain. And these rules can automatically be enforced, and everyone can even verify them since the information is always accessible in blockchain. We then call these apps DS, and smart contracts plays a role as a backend. Later, DeFi, a kind of application that serves as a traditional financial product but works on blockchain, has started thriving since 2020 because people now have easy, which means that everyone in this world with the internet could use secure and reliable ways interacting with so-called financial products on blockchain. So in the beginning, I have told you that both Web 2 and Web 3 have shared a lot of similarities. Here's the diagram showing you that a similar part. In Web 3, we access apps through the browser that we do in Web 2 in order to talk to the backend. In Web 2, backends are programs written in backend languages. Likewise, in Web 3, backends are programs in terms of smart contracts written in language that were supported by the blockchain. Additionally, we store data in decentralized node in Web 3, and we store data in database in Web 2. But where do we execute smart contracts? It is within Ethereum VM, also known as EVM. So the EVM executes as a stake machine, which means that its primary interaction is moving short-lived temporary values to and from a push-down stack. A smart contract will then be compiled to a binary program composed of a series of EVM OP codes, like inclusive for, and, add, sub, and central. Each EVM OP code is 1 byte, and therefore we can have up to 256 different OP codes. Currently, EVM only supports around 141 instructions. What could be the most important philosophy of EVM is fees, which is a specific amount of gas that needs to be used to finalize certain instructions. As a result, gas is the minimal requirement to be fulfilled in order to complete a transaction, and each programmable computation is intrinsically bounded by it. So, all right, now we have basically understood some terms and the whole story. What could lead to security issues in Web3? Let's take a look. So the front-end part is just like what we have mentioned earlier, that both Web 2 and 3 take this as an interface for people to interact with what is behind. We use the front end to give people good UI and user experience to let them access what we want to offer in Web 2. And likewise, we also take the same method in Web 3. Therefore, the end users will need to understand anything beyond their imaginations, and they just need to go on, and that's it. But here comes the problems. It means that the same threats applied to Web 2 could also affect Web 3. Here are some cases. We have 3 cases here to show you how attackers could try to exploit the front end. The first one is cross-site scripting issue on Raritable's NFT marketplace. By exploiting cross-site scripting vulnerability, bad guys can do almost anything they want on the page. And the second one is about DNS cache spoofing attack. By exploiting this, attackers can hijack Curve Finance websites and inject malicious code on HTML. And the last one is UI spoofing, which we're often seen in Web 2. But this thing can be more complicated in Web 3, because the components the bad guy wants to spoof is the function signature. For smart contracts, functions code in the EVM are specified by the first 4 bytes of data sent within a transaction, and these 4 byte signatures are defined as the first 4 bytes of the keychuck of the canonical representation of the function signature. As you can see here, the 4 byte signature were recovered by MetaMask, a famous crypto wallet, to its original function signatures with their best effort. By doing this, users will be able to understand what they are going to do with the contract code. And this is how it works typically, and users in Web3 are already familiar with this process. However, in this case, the bad guy named a function claim reward, but do other things under the table. People wouldn't notice it in the first place, since the function should do its job by its name. It is for the culture. So you should be able to understand why you could use what you have learned during this conference to do security things on the front end in Web3. They are almost identical. Now here comes the part that I want to emphasize today, the security of the back end. First, let's see some cases as usual. As you can see that these are the amounts that attackers try to steal. 3 million, 1 billion. But do you know that in the previous year, which is 2022 solely, roughly 3.8 billion were stolen because of a variety of crypto hacking events according to the report by Chain Analysis. Although this is not so surprising in such new field that everyone are making MVPs first and the security comes after, it is still a thing that we should care in the next few years, especially when there are more people are getting involved. If we are developers, we can take advantage of DevSecOps to enhance our security part of the project. I know that in this time slot, there's another session talking about how you can leverage DevSecOps tools and skills to protect your users. In my talk, I will focus on smart contract security as an offensive player and instruct you to do some basic auditing along the slide. Of course, the first thing that we need to learn is the basics of reverse engineering. It is not that different comparing to doing reverse engineering against x86 binaries or Android app. You still work on binaries in terms of smart contracts. But it is fortunate that if we work on reversing in Web3, everything is accessible and reachable, even if we are doing reverse engineering in black box testing, meaning that we don't have the source code of smart contracts. At first, let's talk about white box testing, meaning that we get to see the source code of the smart contracts. By having a copy of the source code, we can leverage tools to help us audit the code. We have tools such as slither by throw of bits, NathX by consensus, and more. So just for fun, can you spot the vulnerability in the code snippets on this diagram?
Integer, sorry. Is it an integer overflow on allow list? Allow list plus?
No.
Okay.
Okay, anyone? All right. So I just give you the answer to the question. So basically, you can mint as many items as you want because you can see that the price doesn't get updated by the quantity. So you can just mint as many as you want, but just by paying one item. Okay, so as for black box testing, we can always try to replay transactions by copy and pasting what we see on the blockchain. Not always works, but worth a try. By inspecting a transaction, we can also get some useful information and understand internal operations sometimes. We can also take another method, reverse engineering, which is a clear and robust way for us to understand the logics behind smart contracts. So no matter what compiled binaries we have, it is a must to firstly disassemble machine code into disassembly. On the left is the disassembly produced from the bytecode on the right. For example, the first 2 bytes, 60 E0 in hash is to push a 1 byte value, which is E0 on the stack. Then we turn the disassembly into a structure called CFG, which is a very important structure in reverse engineering space. Once we have it, we are able to understand how a program flows, when to branch out in the central. This structure also takes account for recovering the disassembly back to a high-level view of the program. Now you know why I put control flow graph in my slide title. It is so important for reverse engineering. But why do we really need to construct a CFG? What problems get solved actually, you may ask. So there are several reasons. The first is that we want to have correct executing logics. For instance, we have a piece of disassembly here, and it goes from top to the bottom. And we believe that we move ECX times 2 to the position due to line 1. And do 100% sure that is how it ends? Actually, no. We can't guarantee because there may be a jump from some other parts of the program to line 2. And if that happens, we cannot be sure that EX will have the value 2 in it. As a result, when we once again execute the program, the final decision should be based on the register EBX. And by this example, we can use CFG to help us get executing logics correct and produce results that we want eventually. And the other issue is loop. We hate loops when doing reverse engineering because it could make us doing things in loop and waste time. So the definition of loop is a set of nodes in the control flow graph such that there's a single distinguished entry point called the header. Every node is reachable from the header, and the header is reachable from every node, and no edges enters the loop except to the header. I won't go into details about how algorithms works, but in general, in order to find loops, we compute the sets of dominators for each block in the control flow graph. Because it's a tree structure, there will be no loops at all. There's another important component called SSA form that can be converted from a CFG. With the help of a SSA form, we then lift the current abstraction to a higher level one. Okay, so how do we get our hand dirty in making a CFG? We don't. We don't really need to understand every algorithm and theorem to do that. Instead, we can leverage so-called intermediate language-based analysis to do us a favor. Intermediate language-based analysis provides us a unified way to simplify reversing by fitting intermediate representations. All you need to do is to convert machine code to its intermediate representation operations, and the rest will be automatically handled by the analysis itself. We have binary ninjas BNIL, Gijas B code, and so on, and we just need to pick one of them to use. So in the following pages, binary ninjas IL will be demonstrated to showcase how we take advantage of it to reverse a smart contract. To me, I think BNIL is easier to be instructed to complete the task, since it provides Python-based APIs and it is well documented. Good documentation is the king. And this is the sneak peek of what we are having eventually. So we can use binary ninja's API to instruct it to provide the information. The outcomes will be like this. Secondly, we need to tell binary ninja when to branch out, and therefore binary ninja will construct the CFG for us. Having said that, branches information are sometimes hard to be deduced. A common way to infer this information is via VSA, knowledge value set analysis. At a high level, VSA attempts to identify a tight over approximation of the program state for like values in memories and register at any given point in the program. This can be used to understand the possible targets of indirect jumps or the possible targets of memory write operations. While these approximations suffer from a lack of accuracy, they are sound. That is, they may over-approximate, but never under-approximate. By analyzing the approximated access patterns of memory reads and writes, the location of variables and buffers can be identified in the binary. We mentioned that each programmable computation is intrinsically bounded by the guess, and then therefore we can simulate every execution step of smart contracts by giving the context an upper bound of the available amount of the guess. It is crucial for developers to ensure the efficiency of the amount of the guess to be used in the smart contracts. We can count on the fact and take advantage of that to simulate the contract without worries. Because we can simulate all execution paths, we now have accurate values their location could take at any given program points of stacks, memories, and building functions. To simulate the execution, we need a comprehensive implementation of the Ethereum virtual machine. I choose Ethereum.js to help me complete the task. The link and the logo are shown here. Basically, I record every important operations output and store the data to several files so that I can pick up anything that I want when I need them in time. Here is the sample output of the jump table. On the left, we have the jump instructions on 24 in hex. Therefore, the jump table has an array where its 36 elements has all the information that we need. Remember that we said that we could just exhaustively run every instructions. Here is it. We literally run the instructions linearly and record each branch information along the way. We happen to walk instructions in the DFS manner, but it doesn't really give us any beneficial effects, so you can also use BFS. Why not take advantage of this whole thing and getting more valuable information? We can also take note of other interested values, such as inputs of mstore, the returned value of return data size and central. So after getting this valuable information, we can send them through Binary Ninja's API. They are all well documented, so you can just follow the instructions to implement. And this is what we have done eventually. We're now having a functional reversing tool for EVM. Okay, so now let's demo the tool with a smart contract. Here we are given a CTF problem that was released during DEF CON 2018 CTF qualifications, code SAG. The source code for the problems gives us some clues. First is a proxy contract. Through this proxy contract, we will then be able to interact with its private contracts. We mentioned that there's no secrets on blockchain, so we can access the address of the private contracts as well. The user can invoke SAG proxy gamble to play the gambling game in SEG. If the player wins, he or she will be recording in the SEG storage. Then he can ask for the encrypted flag through segproxy.requestPrice function. So it is clear that we need to understand what a SEG contract is and what the game logics are behind the scene. However, the SEG isn't open sourced. What should we do? So without further ado, let our tool do the rest of it for us. So here's the GIF that's showing you that the smart contract is being reversed by the Binary Ninja with our own implementation of the full simulation in EVM. So now we have a clear view of what this contract is trying to do under the table, and we can switch it to graph view for a better view. And then we are given a list of functions that we can inspect, and we click the one that should be the main functions of the gambling game. So as you can see that there's so many functions, there's so many basic blocks, it is so complicated. So we can actually change the view from the disassembly to lower level IL, which is the advantage of being IL. So right now we have a better view of the function, better view of each instruction. But it is still complicated, right? So actually we can further change the view to its much higher level of view. So we can go into the high level IL view. And this view, it will give us more clues about what the contract is trying to do. And this time with this view, it is clear to see that the contract, the function is trying to do some operations in while loop. And there are actually two while loops. So after reverse engineering with the tools that we developed, we are able to write the script to solve the problems. Okay, so what can we improve to make it better in the future with this tool? And I have some ideas. So first, to make it produce more smart contract-like code, not the C-like code, because the C-like code is not intuitive in EVM. And secondly, to have a plugin working like IDAS Flirt plugin. And the Flirt is abbreviated from the Fast Library Identification and Recognition Technology. So with this plugin, we can identify libraries code. And thirdly, since we have a full simulation EVM environment, we want to achieve the goal of semi-automated analysis, which means that we are able to execute partial code in smart contracts in order to observe something at the moment. Okay, so here comes to an end. And thanks for attending and listening to this talk. And thanks a million. If you have any questions, you can just throw out your questions in Slido, or you can send me the mail. And final words, this tool is still in progress and it will be released sometimes this year. So if you are interested in it, you can follow my GitHub account.